Good morning, everyone. Can you confirm that you can hear me? Okay, great. Thank you. We'll start just now. I just wanted to verify before we start. All right, it is 9:30 and we are going to start our lecture. So, welcome to our first lecture on chapter 6. You finished off chapter 5 on Friday, and then we are going to look at chapter 6. And chapter 6 is on complex numbers, right? So we are going to motivate why we need complex numbers, and then we will start looking at their properties and what we can do or what we can't do with complex numbers. You might be familiar with them, but we are going to start from scratch as if you've never seen them. Um, so don't worry if you don't know anything about complex numbers, right? So the first question that we need to ask is, can we invent new objects or number systems? So new objects, for example, when we started off, we in chapter 1 we talked about vectors. In chapter 2 we talked about matrices. So can we invent new objects or new number systems? So we already know about the real numbers. We know there's integers, and so the question is, can we invent new things like this? And the answer is yes, we can, but if it serves a purpose. So uh, mathematicians are not just there trying to create new things that don't have some motivation of solving some sort of problem, right? So if it serves a purpose, yes, we are going to invent new things to be able to explain something or get insight on some objects, maybe even old objects that we have. For example, if we think about this graph, which is y is equal to x squared plus 2. So here you can just imagine this is your 2. We can see that this graph doesn't cut the x-axis, right? For any value of y doesn't come to become 0 here. We don't cut the x-axis. So in other words, if I think of this set, the set of all real numbers such that x squared plus 2 is equal to 0. So basically we are trying to find all the real solutions of the equation x squared plus 2 is equal to 0. We know that because this doesn't cut the x-axis, so therefore it would mean that this is going to be an empty set, right? And so the question is, can we make a new number system that that is going to have this type of equation having solutions? And the answer is yes. We can make a new system that is this as well, this having solutions in that number system, this equation, right? And the answer is yes. What we actually have is this set denoted by that, which is the complex numbers, right? So this is one of the reasons why we need complex numbers. We want to be able to find solutions of equations like this that don't have solutions in the real set, right? In the set of real numbers. And just as a remark, complex numbers were created by this Italian mathematician Cardano, and around 1545, and he was studying cubic polynomials, trying to find roots of those, and then that's how they were created. If you want, you can Google and find out more about that. Okay, so we know why we do need complex numbers, but what are these things? So that's what we want now to get into. So what is a complex number? So a complex number is an ordered pair of real numbers, Z, which is going to be AB. So what we are calling the real numbers here are A and B. So A and B are real numbers, and we are saying that a complex number is a set of, so it looks like a vector, right, in R2, but there are some differences that we are going to see. But it's an ordered pair of real numbers, which can be written like that, right? And so we've got two parts of that ordered pair. We've got what we call the real part. So the real part is going to be equal to A, which is the first component there, and then the imaginary part is going to be the second component, so it's going to be equal to B, right? And so take note as we go. We'll see that we'll change the notation from this to something else much more nicer, a better notation. But formally, when we start, this is what we call a complex number, right? And then so what we call C, right, is the set of all complex numbers. So all the sets of these ordered pairs that we see of real numbers is what we then call the complex, the set of complex numbers, right? And then one thing that we need to note is that the set of real numbers is contained in the set of complex numbers. We'll see this as we go, right? So in the textbook, you see that the presentation is a bit different from what you're going to see, but the point is we don't really like this notation, so we want to go quickly into the notation that is nicer, right? So we'll get into that. So there's a question: is there anything beyond complex numbers? Yes. If you go into field theory, you will see that they are extensions of complex numbers. So you can go and Google field theory and you will find a lot of research on things beyond complex numbers. Right. I'm answering a question from Elias, which is asking, is there anything beyond complex numbers? Right. Okay, so let's see what we have. So before we go on to the beta notation, we are going to define what it means for two complex numbers to be equal, and how to add complex numbers and how to multiply complex numbers, right? So equality, so two complex numbers. So if suppose you've got two complex numbers, Z and W, which are ordered pairs A, B, and C, D. So Z is going to be equal to E. So I'll call this equality of complex numbers if the real parts are equal and the imaginary parts are equal, right? That's one thing there. So remember, the real part would be the first component, the imaginary part would be the second component. So we are saying the real part of Z should be equal to the real part of W, and the imaginary part of Z is equal to the imaginary part of W. That's what we mean. So both cases, both conditions have to be satisfied for us to say that Z is equal to W. And then to add, so if you are to add the two complex numbers, you're going to say, you're just going to add the real parts and the imaginary parts. So you would have the real part of Z plus the real part of W is going to be the real part of Z plus W, and then the complex part, sorry, the imaginary part of Z, which is B in this case, plus the imaginary part of W is going to be the imaginary part of Z plus W, right? And then for the multiplication, so if you want to, so this was adding. Now for multiplying, you see that this is where it then differs from vectors in general, right? You'll see that the multiplication is a bit different. You're going to say AC minus BD, and then that will be the real part of ZW, and then the imaginary part of ZW is going to be AD plus BC, right? Where A, B, and CD are the what we are given there. So you see that this then differs from vectors. Well, in vectors, actually, we actually have either the cross product or the dot product, of which both will not be the same as this multiplication of complex numbers. Right. So let's see. So now we want to introduce new notation quickly, and then we are going to stick to that new notation as we go on, right? So consider the complex number 10, right? So you can see that the imaginary part there is equal to 0, and then what we are going to call I going forward is the ordered pair 0, 1, like that. So the imaginary part is 1, and then the real part is 0 for this one, right? If you are given a vector z, which is defined to be AB, the ordered pair AB, then we can rewrite it as, now that we know how to add and multiply complex numbers, we can rewrite our complex number to be A0 there, and then B0 times the I that we have there. And here you can just verify that B0 times 0, 1 is going to be equal to 0B, right? You can use the definition that we have there. In other words, what we are just saying is this I can rewrite as A0 plus 0B, but 0B can be rewritten as B0 times 0, 1 using that multiplication there. So we end up with something that looks like this. Right. And then from here, what we already know is if you think about the way we defined our complex number, we say the real part is this, and then the imaginary part is that. So if the imaginary part is equal to 0, then we sort of have a real number, right? So what we are saying is, if you think of 2, the real number 2, it can be written in terms of complex numbers. Remember, we said complex real numbers are a subset of complex numbers, right? So 2 can be rewritten as 2, 0. And if you think of 5, it can be rewritten as 5, 0. So this simply means that every real number is a complex number, right? And so once we write our complex number as that, then we need to think about what 0101 01.01 is going to come out to be, right? And if you do the calculation there, you'll see that 01 times 01, if you use our notation, sorry, our multiplication there, AC minus BD, and then AD plus BC, you'll see that this becomes 01. You can verify this. It's not a difficult calculation to do. So if you think of this as AC and then, sorry, this is A, B, and C, D, and then you use the formula that we have been given. Right, so we get that. And you can see that this is actually a real number from what we have said here, that if you've got minus 1, 0, if the imaginary part is 0, then it means that this is just equal to minus 1, right? And once that happens, so we can think of our minus 1. If we were to write it in terms of complex ordered pair, we get something like this. But what actually happens is, if you think of 0, 1 as a complex number, what we have actually gotten here is that z squared is equal to 1. So if you think of z to be equal to 0, 1, what it implies is this, that z squared is equal to minus 1, because that's what we found out. But if z squared is equal to minus 1, what it means is z is going to be equal to the square root of minus 1, right? And then, so if you think about our minus 1, the real part of that is minus 1, and then the imaginary part of that complex number is 0. So in other words, remember we called 0, 1 to be I. So in other words, if you look at this and what we have here, what we're actually saying is 0, 1, because we squared 0, 1 here and we got minus 1, is going to be equal to the square root of minus 1, which we then call I, which is our new symbol there. And then from here, we can we'll see that once we fix it like this, then we get a new way of writing our complex numbers. So there's a question. Is it safe to say complex of R is real numbers? Is it a general case? I am not sure about that. I'm not sure what you're saying. Maybe you can rewrite what you mean. Okay, just rewrite. I'll attend to it. I'm not sure what you mean by that. Okay, so we've got this new I. So let's compare, and then we are going to look at addition and multiplication and see if it's consistent with the definitions that we have on top there. So if you've got a ordered pair z which is equal to 2, 3, right? Then its real part is going to be 2, its imaginary part is going to be 3, right? Now let's look at what would be the counterpart of this new notation we want to propose. So if z is equal to 2 plus 3i, then its real part is going to be 2, and then the imaginary part of z is going to be equal to 3. Here, let me stress that when you've got a vector like that, sorry, not a vector, a complex number like that, then what it means is the imaginary part is 3 and not 3i, right? Please take note of that. It's not 3i, it's just 3. You don't put the I. Okay, so let's see what happens. So if I've got, so basically what we are saying is if you've got an ordered pair 2, 3, then in this new notation, this should be the case, that z can be written as 2 plus 3i. So let's see how that happens in general. So if you've got a vector z which is ab, then you can rewrite this as a0 plus 0b, and this is coming just from the definition of addition of complex numbers. And if you factor out your a, you end up with a times 1, 0, and then plus b times 0, 1, right? And here, remember that 1, 0 is just the real number 1, and then 0, 1 is what we are calling I. So you can substitute these two, and you have something like that. And then we can see that this is just a plus bi, right? So from the old notation, the new notation tells us that if you've got an ordered pair AB, then in the new notation, the complex number will be Z plus BI. And the real part is A and the imaginary part is B, which we would expect from the old notation. So it's pretty consistent there. And then now we get into addition to see if it works, and then multiplication. If it works, then we can discard the old notation. So so for us to be able to do the addition and the multiplication, let's just recap what we have. We know that I squared is going to be equal to minus 1, and or I is the square root of minus 1, right? And this is in complex numbers, right? So let's see what happens if we add, right? So if you've got a vector z, which is a plus bi, and w, which is c plus di, so this would be our ordered pair ab and then cd, right, in the odd notation. If we add them, we are going to get a plus bi plus c plus di, like that. And that becomes, if you take the real numbers only, you get a plus c, right? And then the parts with I, and then you get, so you add BI and DI, you get BI plus DI, which is, if you factor out I, then you get B plus DI. And then from this, we know from what we have here that if you've got A plus BI, then you can write it as an odd, in the odd notation, as the ordered pair AB. So in other words, if I've got A plus C and then B plus DI, what it means is in the odd notation, I have to write it like that. But this is what we would expect if we do multiplication in the odd notation by the definition that we had, right? Now let's look at multiplication and see if it's going to be consistent. Right, so we've got Z times W. In the odd notation, we are expecting to find AC minus BD, right? And then AD plus BC. This is what we are expecting from the definition that we were given. And so let's see. Are we going to get that? So if we say A plus BI times C plus DI, we do our normal multiplication, we get A times C, which is AC, A times DI, which is ADI there. And then if you say B plus BI plus BI times C, you get BCI, and then BI times DI, then you get B times D times I squared. Right. Okay, so Elias said you've clarified. Okay, all right. You're happy with that. Okay, great. So we've got this, and now we then apply what we know. So we know that I squared from here is going to be equal to minus 1. So we can replace I squared with minus 1, and then we end up with that. I squared is minus 1, so we just replace, we get BDI times minus 1. And then from there, if we now group the the real numbers, then we get that. And then the ones with an I, we get BCI plus ADI, which if we factor out I, we get that, right? BC plus AD times I, right? And then from the old notation, we know that if we get something like this, then we just take the real part there, and then that will be our first component, and then we take the imaginary part, that will be our second component, and that will be the odd notation. But that is what we would have expected from the definition that we are given. So in other words, this new notation is consistent with the old notation. So we can sort of discard the old notation and continue with this new notation. Right, now we are going to look at properties of complex numbers. What can we do? Can we add? Can we I mean, we know some properties on real numbers that we want to check if they are going to be extended to complex numbers. So, for example, we know that if you've got real numbers, you can add. So, if this is a real number, a and b are real numbers, then you know that b plus a is equal to a plus b, or if you say a times b is equal to b times a. These properties that we know of real numbers, right? We want to see which ones can be extended to complex numbers, right? So that leads us to theorem 6.1.5, which says the following are true. So if you have got two complex numbers, if you add them, they are going to be if you add them, then it's the operation addition is going to be commutative, right? So this is commutativity of addition, right? And then we know in real numbers that addition is also associative. We see that in actual fact, even for complex numbers, we've got associativity of addition also. And then in real numbers, we know we've got an additive identity. And then you'll see that that is the case also in complex numbers. And the additive identity is 0 plus 0i. In the textbook, it's written as an ordered pair 0, 0. But we have changed notation. So we've got 0 plus 0i. And that is the existence of, additive, this is just shorthand here, identity, like that, right? And then the next one is an additive inverse. So we know that if you've got a real number a, then we've got minus a, such that if you add them, you get 0, right? We also have that in the case of complex numbers. And so if you've got a complex number z, then there is a minus z, such that if you add the 2, you get the additive identity, what we got here in number 3 there. So this is existence of additive inverse, inverse, right? And please, if you have questions, feel free. I didn't mention this, but you already know. If you've got questions, just post them in the chat. I'll check them out as I'm going. Right, so we also have the additive inverse for every complex number that you have. And then now we move to multiplication. So we'll see that for real numbers, we know that a times b is equal to b times a. We have this for complex numbers also. So this is commutativity of multiplication, like that. And then we also have associativity of multiplication activity of multiplication. Right, and then in real numbers we know we also have a multiplicative identity. So if you've got a number 1 times a, we know this is going to be equal to a for any a that you pick. This is the case. And if you think about the real number, if we are writing it as a complex number, it is just 1 plus 0i. So that multiplicative identity for real numbers is just extended to complex numbers, right? It's the same multiplicative identity. Here we just rewrote it as a complex number, right? So we've got that. So this is existence of multiplicative identity, right? And then we also have the distributive law, right? So distributive law. So if you've got z times w plus y, then you've got that is equal to z times w plus z times y. Right, so this will be left as an exercise, so you can go and do this, prove these statements. We're just going to do one, just for you to see how to approach them, right? So before we start the proof, there's a question. Is the standard form of complex number the ordered pair form? No. So the standard form is what we have now, which is this form, not the ordered pair. If I remember correctly, let me just verify for a second. But basically what you need to know from this point onwards, we are not going to use the old notation. We are going to be looking at the new notation. Right. So the a plus bi, yes, I'm correct. The a plus bi is the standard form. This is the standard form as opposed to the old notation. Right. Okay. So let's look at the proof of this property number 5. So commutativity of multiplication. So you know that z is okay. So you start by saying let z be equal to a plus bi, and w be c plus di. So for us to find out what if these are going to be equal, we just have to do the multiplication. So a plus bi times c plus di. What is that going to be equal to? It's going to be AC plus ADI plus BCI plus BDI, right? Sorry, plus BDI squared. And then if you simplify that, you get minus 1. So you end up with AC minus BD, and then plus AD plus BC. Right, and now we want to check the other one, the other multiplication. So you've got C plus DI, and then A plus BI, right? And then you say this is CA plus CBI plus DAI plus DBI squared. And this becomes CA, if we simplify that, that is minus BD or DB. You can just put BD here. Sorry, I want to say DB. DB plus CB plus DA times I, right? But this, if we look at property number, sorry, not property of real numbers, not properties that we have on the theorem, but properties of real numbers. We know that this CA is going to be equal to AC, DB is going to be equal to BD. This happens for all real numbers, right? So we can use that property of real numbers to say this is just AC minus BD, and then plus we can, and then so here we use the fact that this is commutative, the multiplication is commutative, plus the addition is commutative for any real numbers, right? So we then end up with AD plus BC by using the two properties of real numbers. And then if you look at that and that, those are just equal. So the left-hand side is equal to the right-hand side, and so therefore the statement is true. Right, so you can go on and look at all the other properties there. It should just be routine calculations to find out, to write the proofs. Right, using this new notation that we have. So the next question is, where does I lie on the number line? So remember, we've said C is just an extension of R. We know that complex numbers, R is just a subset of that. So where does it lie? Where does this new I lie on the number line? So it turns out that we can't actually we can't represent this on our normal real line, right? We actually have to have a plane to be able to represent these new objects that we have called complex numbers. And this brings us to what is called the complex plane, or the Argand plane, from the mathematician who introduced them. He's called, I think, Jean Argand, French mathematician or Swiss. And if you want to know more about him, you can go and Google on him. But otherwise, we have to represent these in a plane called the complex plane. So the difference between this and R2 is here we have two axes. We've got the real axis and the imaginary axis, as opposed to x and y, the normal that we are used to, right? So this is the complex plane, and I just have a few complex numbers there that we want to represent in this diagram, in this plane, to see what would happen. I'm sure you can figure out what happens. So you've got the real part and the imaginary part. So the real axis, imaginary axis. So you take the real part and you plot it here. So for example, we want to plot this one, 3 plus 4i. So we take the real part, which is 3, we are here, and then we take the imaginary part, which is 4, so we end up with our vector z being there. Sorry, not vector, used to vectors. Complex number z would be there, right? So it's just a point there. And then if we want w, which is 2 minus I, so we go on to the real part, it's 2. The imaginary part, if we say this is our minus 1 there, then our point will be somewhere there, which would be our w. There's no bar on top, because bar actually means something else that we are going to talk about. Right. And so that's what we have. And then if you want the complex number 3, which you can write as 3 plus 0i in complex form, in the standard form, then we can say the point would actually be 3 here, and then the imaginary part is 0, so we are still here, because the imaginary part will be there, so we are here, and that becomes our y. So that is the complex number y there. So just for you to have a picture of what it would look like. We would go into more details when we get into section 6.2 on this. Right. So let's go on to look at some notation. So if you've got Z, which is 3, 5, then from what we have in the, we know that we've got this minus Z. So what is minus Z? It's a complex number such that if you add it to Z, you get the complex number 0 plus 0i, right? And then, so you've got Z, which is 3, 5 in this case, or let's put it as 3 plus 5i. Then minus Z, so let me remove that and put that. Then minus Z, for you to be able to get 0, 0, if you add to Z, you just need minus 3 minus 5i, like that. And that becomes your minus Z in this case, right? And if we say Z minus W, what we just mean is Z plus the minus of W, right? And then if you've got Z to the power N, like in numbers, you are going to have to multiply Z, the complex number Z, you multiply it N times, right? So that's just some notation there. There's a question, can we express imaginary numbers in 3D? I don't think so. I don't think that is feasible. Unless, well, unless there is another coordinate. So, but no. I think if so we can express them, but I think the question is always what's the point? So we are trying to sort of just going back to what we have. If it serves a purpose, maybe we will need something like that. At this stage, I don't think there is any sort of mathematics that deals with. So you're sort of saying you've got a complex times some real number or something like this. I don't know if there's any use of that at the moment. If there's use, it will probably come in handy if it's needed. But at this stage, I don't think there's any need to do that. So yes, we can, but we don't have any use of it. So probably there's nothing, no theory on that. Right. So we've got some notations and well, so some conventions of, okay, what is minus Z, what is Z minus W, what is that? Now let's get into division of complex numbers. So we know that we cannot divide vectors. We could not define, if you remember when we looked at vectors, we didn't define division of vectors. And we cannot divide matrices. We didn't have a definition when we looked at it. We had inverses, but not quite division of matrices. And then we know we can divide real numbers, at least the non-zero ones. So for example, if you've got 6 over 3, we know this exists. Or you've got 2 over 5, this exists in real numbers, right? Provided the bottom part is non-zero. Then the question is, can we divide complex numbers? Right. And the answer is yes, we can. And that is going to be part of what we are going to look at. And the next question is, can we also find inverses of complex numbers? And again, the answer is yes, because once you can divide, you can sort of think of how to find inverses of complex numbers. So there's a question. They are called hypercomplex numbers, but are abstract. Oh, okay. I didn't know that. Thank you, Chris, for that. I've never looked at them, but I guess they serve a purpose. So, as I mentioned earlier, if they serve a purpose, they're going to exist. So, thank you, Chris, for that. So, Elias, you can go and check. You just Google hypercomplex numbers and see what they look like. Right, or what is the point of them existing? Right, so now we get into, we want to find out how do we write these inverses of complex numbers and see how we can divide complex numbers in the end. That's the main goal. Right, so again here, remember that when we are looking at real numbers, we want the denominator to be non-zero, right? That's the only way we can divide. And in fact, if you think of a multiplicative inverse of a real number, you want the real number to be non-zero for you to be able to find the inverse. So likewise, we also need, for us to find inverses of complex numbers, we sort of also want non-zero complex numbers. So we know what non-zero real numbers look like, but what are non-zero complex numbers? And this leads us to the next definition, which is what is a non-zero complex number. So if you've got a complex number z, which is a plus bi, where a is and b are real, then we say z is a non-zero complex number if either the real part or the imaginary part is not equal to zero, right? So if both of them are zero, then we have a zero complex number. But if either of them is not equal to zero, then we have what we call a non-zero complex number. And so let's see what we have. So as I mentioned, for us to find this this inverse of a complex number, we want to be able to find, we want the complex number to be non-zero. And so this leads us to theorem 6.1.10, which tells us that for any non-zero complex number, the inverse exists. And here when we say the inverse, we are talking about the multiplicative inverse. So a complex number such that if you multiply with z, you get our multiplicative identity, which is 1, which you can think of as 1 plus 0i. So I'm just going to quickly do the proof, and I think that will be the end of our lecture. We'll continue with 6.1 tomorrow. So let z be equal to a plus bi, and w be equal to x plus yi, where a not 0 or b not 0, right? Because we want this to be non-zero, as we said here, z. So that's why we need these conditions there. And then x and y are just real numbers, right? By definition of a complex number, right? And so what we want to check is, can we find some w such that zw is equal to 1, right? This is what we want to check. So we are saying let this happen such that this happens. So we want to check if it's going to be true for any z that you have picked. So any arbitrary a, b such that a is not equal to 0 or b is not equal to 0. And if we do that, then we end up with a plus bi, which is like that, which is equal to 1. And if we do the calculation, I'm going to leave the calculation here. So we've got ax minus by plus bx plus ay. I is equal to 1, right? But 1 can be written as 1 plus 0i, as I mentioned here. So now for us to find, if we can find these values x, y, and in fact, what we want is to find, yes, we want to find x and y such that this happens, because a and b are sort of fixed. So we want to find x and y such that this is true. So if we have that, then we can say, well, we can compare. We know that these are two complex numbers that are supposed to be equal. So if I take the real parts, then they should be equal, right? So in other words, ax minus by is equal to 1. And the imaginary parts, which is bx plus ay, is going to be equal to 0. And then from there, we then say, does this look familiar? Well, it does, because this looks like a system of linear equations. So in other words, we can rewrite this as ax is equal to b, where these are vectors. And what is our a in this case? So x and y are the variables that we have. So we say a is going to be equal to these coefficients. So we've got a minus b, b and a there. And then we've got our vector x, which is xy, our variables. And then b, if you look at this side, is going to be equal to 1, 0, right? From what we have there. And so the question is, when can we find this to have a solution, right? We know that for x and y to exist, this system has to have solutions. And for this to have solutions, what it simply means is the determinant. Remember that the determinant of a, if we find that the determinant of a is not equal to 0, then we know that we've got a solution, a unique solution, in fact, for this system that we have. So let's look at the determinant of this. So the determinant is going to be, so the determinant of a is going to be equal to a squared. So a times a minus b times b, right? Which is equal to a squared plus b squared, right? That is the determinant of this matrix. But what is a squared plus b squared? If we look at the conditions that we have here, we know that at least one of them, either a is not equal to 0 or b is not equal to 0. So in other words, if I think of a squared plus b squared, it has to be greater than 0. And in fact, that means it's not going to be equal to 0. So because of that, we know that by theorem 2.5.25, the system has a unique solution. So therefore we can say the unique W that we get is such that ZW is equal to 1, and that is it. So that is the proof of this theorem, and I think I'll stop here. Our time is over. We've gone overboard. So thank you. If you have questions, I'll stay behind for a minute or so. Otherwise, enjoy the rest of your day. Thank you. Okay, it seems that there are no questions. So thank you for attending. Enjoy the rest of your day. Bye.